Okay, in 2.1 part 2, we're just going to look at two topics, and that's domain, and we're going to look at a few story problems. So domain is simply all inputs of a function, so it's all of the values you can plug into a function. So for the first one, if we look at x cubed minus 1, I sketched a little picture of x cubed minus 1. It's just a cubic shifted down 1 unit. And if you think about a cubic on a graph, you can plug in any number. In fact, the arrows tell us that it extends in both directions and up and down infinitely. So we know that there are no restrictions. But if we look at that function and, let's just look at a few numbers. Can we plug in negative numbers? Yes. Can we plug in 0? Yes. Can we plug in positive numbers? Yes. Can you plug in radicals? Yes. Fractions? Yes. So you can go through those things. You won't find something you can't plug in for x. And sometimes these are harder to identify than domain restrictions or ones where you can't plug stuff in. So that one's just that. It's just simply domain is all real numbers, and we use that double-lined R. It's the shortest way to say that. So if we go to another one, f of x equals the square root of 1 minus x. So it's a radical, so we know we can't have negative numbers under there. We also can't have, well, no, just negative numbers. We can have 0. So instead of thinking through that and trying to write it out without actually solving it, the way to do that is just take that outside of the radical and set it to greater than or equal to 0. We simply solve this inequality, and that's going to be your domain. So if we added x to both sides, we get that. And if we just reverse it, because I like to look at it when the variable's on the left, x is less than or equal to 1, that is our domain. And you can test that by plugging in numbers that are negative in for x into the original function here. And if you plug in negative numbers, that sign's going to flip because it's 1 minus a negative number, so it'll be positive. So that makes sense. But really, you don't have to think too much about it once you solve it because that is simply the domain. If we look at f of x equals 1 divided by x squared minus 2. Well, this is a denominator. So, I mean, that's our situation there. So the denominator can't be 0. So these are a little bit easier because all I like to do is take that denominator. The only thing it can't be is 0. So we set it to not equal 0. And then we just solve for x. So if we add 2 to both sides, get that, take the square root, and we get x. And I took a square root, so I have this plus or minus root 2. Okay, so those are the numbers that x can't be. So that is not your domain. Those are things that are outside of the domain. So this one's a little bit different to notate, and there are other ways to do it. If this doesn't make sense yet, don't worry about it. We'll get more practice with this. But the way you do this is say, well, values x, this vertical line means such that. So it's x values such that x does not equal, and then we just list those, plus or minus root 2. And so that would be called set builder notation. And you don't often have to use that, except for cases like that for what we're doing. So to sum this up, the simple statement here is there are two cases to look for. And that's denominators and even roots. And what I mean by even roots, if you look at the second example, this would be a 2, right? So 2 is even. If that number is a 4th root, 6th root, 8th root, those are ones you have to check. If it's an odd root, you don't have to check it because you can plug in anything into odd roots. Okay, so we're going to look at just a couple more domain problems. Okay, f of x equals the square root of x squared minus 9. So this is similar to that second example. What we're going to do is just take x squared minus 9 out of the interior of the radical, set it to greater than or equal to 0. Let's factor it. This is a difference of squares. And with these, it's a little bit different. So what we do is create a number line. And we just put those two values on there. So for that, we would have -3 and 3. And what we're going to do is test values above 3, between -3 and 3, and below -3. Okay, we're going to plug those into the original function. So one of those numbers that I'm going to choose, a number between -3 and 3 is the easiest one. So f of 0 into the original function. Okay, that's going to give me the square root of -9. So we know that numbers between that -3 and 3 are not going to be in our range or in our domain. And then we just check numbers above and below. So let's go below -3. Same thing. We take the -4, square it, minus 9. That would be 16 minus 9, or root 7. So below -3, this is going to be positive, right? And if you look at this inequality, what it's asking is for numbers that make this expression greater than or equal to 0. So we're looking for positive values out. So this one works. If we go 4, it's going to look the same because that 4 is going to be squared minus 9. That's also going to be root 7. Okay, so this would also be positive. So I'm going to write this domain in a different way because I'm really trying to show you different ways to write domain. Please don't worry too much if this isn't clear as to how I'm writing it. So here's another way to write this domain. And I'm referencing these, what I just circled there, that represents your domains where it's positive. So the domain is all numbers less than -3. So you're going to have -infinity up to -3, including 3. And this U means union. And from 3 to infinity. So if you look at that, what this does is it excludes the numbers between -3 and 3. And so that is your domain. And if you don't get this part in this particular assignment as far as writing those domains, don't worry about it. If you get here, this is that means that you understand what we're doing, and then we just have to clear up. We're just going to clear up how to write those domains later, so I wouldn't worry too much about it. Okay. So that's a domain. That's a little more complicated to do, and you have a couple of those assigned. Let's go into our next little section here. So the story problems in this section are application problems. They're pretty straightforward. They look a little difficult, but they're really not. They are not the worst application problems ever. Okay. So example 5. If an astronaut weighs 130 pounds on Earth, then her weight when she is h miles above the Earth is given by the function. So h represents height. That's distance above Earth. So for the A part, it says, what is her weight when she is 100 miles above Earth? Well, that's just simply saying plug in 100. Okay, so 3960 plus 100, and that would be squared. Okay, and so these are calculator problems. If you get something like that, I don't expect you to do that by hand. So I've worked these out already. And if you ever see an error in my notes, just send me an email because I can adjust, well, at least, adjust it in my written notes. So this would come out to approximately 123.67. And this is in pounds. So that makes sense because if you're further away from the Earth, then you're going to weigh less. The B part. Construct a table of values for the function w that gives her weight at heights from 0 to 500. What do you conclude from the table? So if I just draw a table here, this is what it's asking. Okay, at different heights, what is her weight based on that height? So I've already plugged some values in here, and it doesn't say how many values to plug in or anything like that. You're supposed to choose them. So if she's on Earth, and I plug in a 0, so that's not above Earth, right? This is, if you plug in a 0 for H, it will come out to 130, which makes sense because that's what she weighs on Earth. So I know that, what I just did makes sense and it works. If she is 100 miles above Earth, we just did that, 123.67. If you plug in a 300, and this would all be done on a calculator, and I'll get into that a little bit later about how to create tables and all that stuff, because you wouldn't have to do this by hand. This comes out to about 112. And I also checked at 500. I plugged in 500 for H, and I got 102. So as we go down this way, we increase height, what's happening? And hopefully it's obvious, the higher she is, the less she weighs. Okay, so that's a pretty basic one where you're just plugging in numbers. Some of your problems are like that. Okay, the next example we're going to look at is from your problem set. So for the A part, well, first let me read this. So due to the curvature of the Earth, the maximum distance d that you can see from the top of a tall building or from an airplane at height h is given by the function d of h equals root 2rh plus h squared, where r is the radius of the Earth and d and h are measured in miles. So that part is important, and this is going to come up a lot. So that's measured in miles. So d of 0.1, let's check that. This is really just plugging in these values. So d of 0.1 is going to be 2 times the radius, which is given, 0.1 plus 0.1 squared. So I already worked these out. These are calculator problems, and we'll get into calculator entry more and more as we go. But right now I just want to, look at these solutions. So 28.1 miles is what I got. Okay, d of 0.2 is the same type of calculation. Let's plug it in. So 2 times 3960.2 and 0.2 there. So if I simplify that, I get around 39.8 miles. And that would make sense because 0.2 is higher in elevation than 0.1, so we should be able to see further. Okay, so for part B, how far can you see from the observation deck of Toronto's CN Tower, 1,135 feet above the ground? So like I said, this is in miles. So the function is in miles, so we need to convert it. So convert, I'll write that out. we're going to do a lot of conversions. So 1 mile and 1 mile is 5,280 feet, and we want to clear out the feet, so we put it over 1. And the way this works is just you multiply straight across, divide by, well, you multiply straight across, then divide. So cancel out the units, and this would come out to 0.21 miles. So it's going to be pretty close to what part A was. So if we plug in 0.21, it's the same calculation again. It's 2 times 3960 times 0.21 plus 0.21 squared. So this gives me something like 40.8 miles. Okay, so you should be able to see a little further at 0.21 versus 0.2. So it looks like we're doing that correctly. So C, this is getting a little repetitive, but we'll finish it anyway. So C is commercial aircraft fly at an altitude of about 7 miles. How far can the pilot see? So that's in miles, so it's just to plug in 7. Okay, and just calculate that using a calculator. The first time I did this, I got 235.6 miles. So at a height of 7 miles, you can see for 235.6 miles. All right, so again, if you ever see any miscalculations in these, just tell me, and I will adjust those or send out an adjustment. All right, so if you have questions, contact me. Thanks.